Our first speaker up this morning is John McCoy. He is not speaking about hacking NetHack. He is speaking about hacking .NET applications. So let's give him a warm welcome.
Thank you, and welcome to BlackHat. Freudian slip. So this is an example of what you can do to an application. I've injected 3 applications, one of them being a supposed Facebook hack, which is actually malware, Aircrack, their GUI, and Parabens forensic software. And I've turned them all into essentially one application and intermixed them. And you can move objects from one application to another. You can attain pretty much full control over your target and treat it as if it was your own or any number of targets. And fortunately, all the buttons still work and behave just as they did. And this shows you the Facebook about. And they're all nicely packaged into one cohesive application. And that's kind of what I did last year. Instead of talking about that, I took off the close button. So let's close this real quick. One of those last minute playing arounds, right? There we are. So this is hacking .NET applications, the black arts. I'm going to be going into detail about attacking applications and what it takes to make cracks, keygens, all of these black arts, quote unquote. I'm going to be going into making malware for your own purposes of practical jokes or more ability into your target application or obviously malicious purposes. This is PowerShell and something that I wrote last couple of days just as a nice little demo of what you can do to PowerShell and that it still functions, it still works. You could put a keylogger or whatever you want, but this is where it's going, to be able to fully control any .NET application as if it was your own. And this isn't going to be new or different than what you might see done in the old days against C++ applications, where you spin up IDA Pro and you play with some heap pointer manipulation, but it's in .NET. And this is targeting .NET applications, obviously. It's a factor easier in .NET, and there wasn't anything attacking .NET, so that's why I'm here. And like I said, welcome to BlackHat 2010. It's looking like a pretty good year. I guess I'll talk for one more minute. Fundamentally, attacking .NET applications isn't different than going after something written in, than going after something written in assembly language or C++. Once you have legitimate access to your target, the memory objects are yours to play with. Whether it's Python or Java, it's pretty much the same. Specifically, runtime languages have a lot of the same abilities as .NET, so a lot of these attacks will one-to-one carry over to .NET. When you try and do this against C++, the concepts will carry over, but the actual implementation of your attacks are drastically different. And like I said, it's a factor harder in non-runtime languages because I'm using some of the core abilities of runtime languages, such as reflection, being able to walk around memory and not have to parse it. You can just ask the program to parse the objects for you. Cool. I'm going to cover how to attack .NET applications, tools and methodologies of attacking, overcoming quote-unquote secure applications, building keygens, cracks, hacks, and malware. And I'm going to touch on reverse engineering for defense. Kind of the best offense is a good defense, right? And I'm going to break it down into 2 separate and distinct areas of attacking in memory and attacking on disk. They share common technologies, but they're wholly different attack vectors. The attack overview. When you attack on disk, you access the logic and decompile it. You infect the logic and you drop your shims in and you gain your access to your target. And you hook the logic and you test kind of in a iterative life cycle. You want to know that you're attacking the right objects and your state that you're looking at is correct. Attacking in memory. You inject into your target, navigate its structure, and edit and control your structure. This is how these are completely separate attack vectors. Instead of going after code on disk, you're going after objects in memory. And they achieve essentially the same goal, but from different vectors. Attacking on disk or in memory, I like to break it down into a similar attack flow of you do your reconnaissance. You understand your target and you understand what it's made out of, what technologies might be stopping you. You gain access to your target. You get past whatever security mechanisms might be in there, and depending on whether you're on disk or in memory, you're going to get past those and gain access. I'm attacking assuming that you have rights to the machine, assuming that you have the rights to inject into an admin process from another admin process. I'm not elevating, I'm not dealing with any compromisations. I'm more post-exploitation. Once you get into your target and you have legitimate access, that's where I come in. You identify the weak spots. You want to find where it's easily malleable, where you can break the logic, and from this point forward, it's going to be yours, and you're not going to have ripple effects from affecting your target. And then finally, controlling what you need. Easily gaining access to a login screen or whatever to control that command to the server and subverting it or attacking it. Attacking in memory. I've developed Gray Dragon, which is just yet another injection system specifically built out of .NET technology to show how .NET can do injection. It uses a little bit of C++, but it's 90% .NET. And it specifically delivers payloads that I've also crafted that I'll get into later. And this is a random program that I thought I would show that this is Gray Dragon, and this is a file deleter that securely removes applications, files from your machine. I wrote a nice little payload that I'm not going to be distributing, that instead of deleting your files, it sends them up to the internet and then deletes them. And to give kind of a scope for this, to do something that subverts an application takes 2 hours or 4 hours for a medium to high grade programmer. This isn't something that you're going to have to dig through a bunch of assembly language or anything like that for. So I drop in a payload that allows me to control the application. It does things like go through and change all of the strings, delete. This is an idea of how you can affect the objects in memory. This is affecting the GUI, but you can just as easily go and affect timers or SQL connections, whatever. And I'll get to this later why this is important, but I can ask this button what code it fires. This is a highly obfuscated application that's well defended, but here's the class, this weird string, and here's the function. Music symbol, new line. And you can jump straight to this function and read what this unlock button does. And this unlock button, of course, points to process the registration code to see if it's valid. You deobfuscate this one function, and that's the entire validation sequence for this program, for registering. And that's what Gray Dragon does. It quickly gets you into your target and delivers a payload. It uses a C++ bootstrap that will then load a C# bootstrap, and this in turn allows us to choose whatever arbitrary payload we want. Once we get into memory, our arbitrary payload can move around the target freely and completely manipulate. I haven't found anything that it can't manipulate with enough work. I've also developed a fake keyboard USB device that comes in, types in a payload into PowerShell, and then PowerShell unpacks Gray Dragon and then injects for a nice little round trip that comes straight from a USB keyboard. So for all you forensics people, how did the program get on there? It could get on there purely through a keyboard insertion or someone switching out the keyboard while it was off. I did a nice Metasploit payload last year, so you could drop in over Metasploit. and be able to target application X on machine Y and get in there. And I did a SQL Server Management Studio hack that attacked the login sequence, and instead of logging you in, it would change your password and Twitter your old and new password, username, and IP address. Just for fun, right? When you attack at runtime, your executable has keys and security mechanisms that say, yes, this is your valid application. It loads valid DLLs. This goes through all of the security systems of Windows and eventually becomes a process. This is why we attack in memory, because the security systems have all fallen away at this point. We inject into memory and we're in. No matter what security verification, it all checked out. Maybe it went up and did a little bit of whitelisting, or it checked in with the server to make sure all of the memory objects are pure. Whatever it is, at the last second, we inject in and we drop in our hacks, cracks, malware, backdoors. This is the power of injecting in runtime over attacking in disk. You don't have to worry about all of these security methods, mechanisms that people put up against you. You gain full access. You reverse engineer it to get the map of your program as much as possible. When you understand how the program is constructed, you'll understand how to attack it. You attack it in memory, take out any security that might be there, and then control the program. It's pretty much that simple. You can, for the most part, with an unprotected program, probably 2 hours, you can have a working attack that is going after a login screen or a SQL connection. For you that came in a little late, I just did this a little earlier, but this is Parabin's forensic software that I'm going to inject into. It's an OK protected application. It has the standard, here's your registration key, here's your USB dongle, and trying to make sure that this is used in a forensically sound environment, all that. However, when you dig into it, you'll find that just like every other .NET application in existence, it's fundamentally vulnerable. We inject into it, and it brings up our .NET shim loader. I called it Slate just because I didn't have a word for it. And we can load up any number of applications. This is a piece of malware that I found that I injected in. And this says that it'll attack a Facebook password, and it actually attacks you. This is AirCrack. I went through and injected these 3 applications into one. They're injected into the same memory space, which means they can fundamentally share objects. You don't have to do some sort of weird DLL sharing and pass in between processes, because I injected these all into the same one. And then I deploy a payload that goes through and adds buttons to every form that it finds. These buttons just do some standard thing. This is how I start when I attack an application. I drop this in here, and it allows me to edit something, where I can say, I want you to bring up an editing window that will allow me to retool this. And you can just go through and edit whatever you want. You can change whatever objects you want. But the main purpose of this payload is to get you quickly to what this launch button does, or being able to pop this launch button off of one application and put it on another one, and they still function. One of the nice things about this is you can combine multiple applications, and they still do their original task. If I choose something here, then it will resolve on the original application. And so you can cleanly do this. You're not worrying about heap pointer manipulation. You're not worried about crashing something, because you're literally changing .NET objects that are built to be secure, that take into account multi-threading and the like. I mean, of course, I'm playing some weird games to be able to move these between these applications, but fundamentally, it's clean. It's not going to give you instability. You're not going to have to worry about it 20 minutes later because you've changed the logon box. This was a lot of my talks last year, hacking .NET applications, a runtime attack, where you basically control the objects of your application so you control the application. I talked at a number of conferences. I gave an arsenal here at BlackHat. I talked at DEF CON, AppSec DC, DojoCon, and a few other conferences. I have them up on my website, digitalbodyguard.com, and you can check them out and watch these. I go much more in depth into attacking in memory. But this talk, I'm going to focus more on attacking on disk, because this is what you want to do if you want to make hack cracks, keygens, all that. You want to go at it on disk. You want something permanent that you can affect your application and drive the point home that you own it. I created Grey Wolf. It's another decompiler for .NET, but it's a little more tooled to what I needed. I found that most decompilers didn't have the tools and functions that I needed to attack applications, so I ended up writing my own to accomplish what I wanted. So this is Grey Wolf, and an arbitrary application that will drag and drop in there, and it decompiles it. Decompiling it gives us access to the namespaces and the source code of our target. .NET, being a runtime language, fundamentally isn't compiled until runtime. This is one of the things that makes round-tripping an attack much faster. That it's fairly a one-to-one comparison between what's on disk and the original source code. And this is the source code of a compiled executable. This application that I'm going after simply, at this point, brings up a password validation box, and it fails. Since I don't know the password, it doesn't let me in. Since we're attacking on disk, and the point of this is to attack and compromise, this is the isPasswordValid function. It passes in a salt and a vector. It takes in the password you entered, does some real heavy crypto, and all of this comes down to, does it match the text, which turns into a Boolean. And this is the spot that we're going to go after. This is IL, which underpins all .NET applications. It's essentially source code, but it's a little one-off. I'll add a couple of no-ops to clear me some room. I'll push true onto the stack, and then do a return. So now our password validation looks like this. Return true. That's your password crack. We save this out, and that's it. We now have a cracked version of this back here. Type in something, and it validates. That's it. 6 or 7 clicks. This application happens to pack and have a second layer of crypto, but that's getting past a good 40 or 50% of the marketplace of your cracks, going up against your validation. I'll get more into Grey Wolf and the features that it has, but that's why it's faster. It's specifically tuned to get you into your application, get you to IL, and be able to change it. You're attacking on disk. You open and access your source. You decompile it, you gain access to its base technology. You infect it, and you change your target's code base. You exploit it to take advantage of its weak spots in code and architecture, and you remold it. That's it. It's pretty much a quick round trip, assuming that you're going up a weak architected application with minimal protection. The weak spots that you want to go after when you're attacking an application to develop your cracks, you can flip a check. You can set a value to true, you can cut the logic, you can return true, or you can access a known value inside the application that you want. Simply registered equals true is very effective. There's a good number of applications out there that will register your application. Or in the case of a password check, I could have said, does A equal B? Instead, does A not equal B? And only invalid passwords will get you through. And these are easy to implement. Within that, put a true on the stack and return, it's just as easy to do these. Is registered, like I showed you, put your return true at the top. Is valid key, return true. You cut the logic, say on a SQL cleaning, and all of their good security is now completely subverted with returning the original string. Is valid password, you want to access a known value because you want to know what password it's validating against. You simply show it to the user, and there's your password. I'm going to attack Microsoft Media Center just as you can see it going up against a real application that you know isn't made by a third party, no one. When it checks a password inside of it for parental checks, it takes in a string, it takes in the known value inside of the application, it checks to make sure that the known value inside isn't null, that its length is greater than 0, and then it does a check to make sure that it doesn't or does start with a colon. This implies whether or not you're looking at a hash code or a pure password. and then it branches. This checks against the pure value, and this checks against the hash code, which is interesting when you think that a logon screen that should have one pure track has a branch, that there's some sort of an alternative weak spot. Instead, we're just going to put return true. Gray Wolf goes in and does the job. Here is Gray Wolf again. This is the core DLL with all of the logic for Microsoft Media Center. And of course, this is mildly protected and all of that. Doesn't much matter. We come in, Media Center, and I think I wrote that down. There we are. Yeah, Media Center options. Okay. Media Center, it's down in the options namespace. Parental check, and check password. And that's tunneling down into your logic. We simply add again our push true onto the stack, again in IL. It would be nice to someday make this so you can write it in C#, but this is just an internal tool that I wrote to do this. And that gives us our return true. But it doesn't, yeah. I wrote a nice little wrapper that installs it. Installing into a .NET application is a little harder when you're talking about a Microsoft application because it integrates into the GAC. This installs into the GAC. It takes out native images. It reconnects it into the application so it gets called. And that's what this installer does. It's more complex, but I'll get into that much later. So we come into our Windows Media Center after it's been compromised. And it takes a little longer to boot than normal because we've taken out the native image pre-compilation and it has to compile it, which .NET does the very first time that you run it. Come down here into parental controls, and it now shows us our password, and any password works. And that's the basic premise to attacking an application and subverting its protections. This is a protected application. It's signed, it's verified, it's deep inside of Windows, and this could just as easily be Management Console or some other key fundamental firewall rule set manipulator.
What about code that has been obfuscated?
I'll get into that a little later, and it's just as easy. Obfuscation doesn't do anything to you. Keygens, cracks. This is what we're here for, right? When you want to make a keygen, here's what you want to be going after. You want to, okay, go for it.
Is Media Player authenticated sign?
Mm-hmm.
And that doesn't pick up the fact that it's numbered?
You'll be happy in a couple minutes. So, you want to do your crack, right? Here is just like before, this is the weak spots you want to go after. This covers 90% of the marketplace. Every single registration box key that you're going to find will be vulnerable to one of these. Public-private key signing. It basically takes an XML or a command from the server, encrypts it with the public key, pushes it down, and executes it. This is subverted by change the keys. Instead of trying to pick the lock, just change the lock. We can get inside a code and rekey it, right? We can put in our own validation key, and we know it. Gets right by that. The next one you'll see an awful lot for some reason. It takes a name and an ID number, which is your serial number. It does a little bit of math, and then it compares this against a known value. We simply ask what that known value is, reverse it, and then we have the outcome for our key generation. A call to a server. When it calls to the server, you simply hack the call. You can manipulate where it calls. You can manipulate any of the steps within it, and you simply stop it. Demo equals true, you set it to demo equals false. Oddly enough, this works on programs probably written in the 90s that were ported forward to .NET. And complex math, which is my favorite, because it's beaten with other complex math, brute forcing, and simply problem solving. It's a complex math that was never meant to be solved. But of course it is solvable. And it's my favorite because it takes maybe 6 to 12 hours to beat it, depending on how good it is, and it's a good win once you're done. And 1% of the time, you're going to find the keygen inside of your target. Because of some managerial decision, they packaged the key generation sequence inside of the target when they shipped it. This is nice because you can just go in, fire that one function, and generate your own keys validly with its own code. So rekeying it. If you can beat them, why join them, right? There's a complex key, and you simply reset the key. And as I showed you, being able to push return true, it's just as easily done to push your own key in there. Hacking the server call. You have it send to a new server. You have it pick a system ID that's known that you've already pre-calculated and wanted to attack. The software gives a pseudo-random return value based on your system ID and your registration code that you pre-calculated since you own the call, and it registers. That's pretty much all that it ever takes. This is also very important to do when you don't want your software to phone home. The registration replay attack also works, which is really nice. You have John Doe passed in. This gets changed through a complex algorithm, kind of like the complex math. It gives you whatever outcome, it then compares it against your serial number, and simply if they don't match, it doesn't register. We take that known value, and we simply do it again with that known value as our registration code. And of course, it generates the same input value. And good key generators will mess you up a little bit by putting in something that ties in the serial number to the name and gives a different value, but that's also easy to attack. And then simply, they, of course, match. And this works probably against 10% of the marketplace. Complex math, my favorite, you chop up the math. You break it up into as small segments as possible, you attack its weak spots, and any of the hard parts, you simply just use brute force against. If there's two variables at the end that or two characters at the end that you just can't calculate, brute force it until it works. Since you have the validation sequence of your target, you can simply try it over and over and over again quite quickly. And finally, whatever is in between you and that complex math to success. Here is a key that I wrote, kind of. This key is based on some of the applications that I'd been attacking. I took 3 applications and combined them into one to give you a sense of what it takes to crack a keygen and what a keygen looks like, because for conscionable reasons, I didn't want to push out something that would open up Microsoft's new product line. So you simply ask the button, what do you fire? Here's the function that you would go to with your grade wolf to get the source code to pull it back, and the corresponding keygen that comes with it. The interesting thing about this is when you're inside looking at your key generation code, it gives you a good perspective of how well they protected their application. To know whether or not they have hardened their application, you can see how well they've protected their key generation. Most applications will break it down into something like key test and check key, which of course, if you wanted to crack, you would put that return true. But to make a keygen, you want to understand what it does, such as they normally put a tagline that this is the version number and the registration level of your application. It then goes and does a bunch of string manipulation. And finally, it does a bunch of complex math, usually raising stuff to powers, doing mods, and the like. This is what you're going to see, and this is on the CD. You can check it out to get a feel for what attacking piece of software's keygen is, and this would probably take about 12 hours to crack. The combined time for all 3 applications that this took from, I think probably took about 14 hours. So that's on the CD, and you can check it out. This is a application that is, for lack of a better word, pseudo-malware. It's a key logger that pretends to encrypt your keys and do a lot of other stuff. I'll get into later on why you want to open up an application. And it, of course, has the password that doesn't work. It has a serial number, all of that. And this is the cracked version. Okay. So Any password works. It divulges the known password inside of it. So if you wanted to know the user's password, there it is. And it brings up. I've went in and rekeyed this to, oh, sorry about that. I have to open it up in a sandbox because it's already registered. So this should rekey to I'm alive, and that's it. I've went in, rekeyed this application ahead of time, and now it responds to I'm alive. You can rekey it to whatever you want, push out your own keys, distribute it, and it's good to go. It uses the built-in validation sequence, so you don't have to worry about it looking erroneous. To dig into code, this is what you're looking at. And the namespace, forms, unlock. And like it came up that this might be obfuscated, this is made slightly harder, but not even a few hours harder. It's pretty much search and replace. But here's where it checks the password. It takes a known value and returns it to the screen. This is divulging the correct password. This is where it used to check the validity of your input password. It's true, and then it returns. The part where it checks the password that I rekeyed is classes. Classes, core, and the constructor. And this is the key. This is the complex value inside of the application that denies you access to the application unless you have the correct decryption key. And this is what allows you to quickly go from a hard-to-break application to a rekeyed application that's completely subverted. This is nice when you want to break something that's third-party and you, of course, don't have access to. These are smaller applications that I wanted to show you. I didn't want to show major applications and hurt some company with this, but this is the same attack vector and about the same level of attack that you would use against an application that costs a few $1,000s. But I didn't want to show them this year. Attacking the IL, it's pretty much the matrix. It's what's underneath .NET. When you go up against an obfuscated application, this is what you want to know. You want to be able to read and write IL. If you're going up against something in .NET, it's pretty much the new assembly code. It has stacks. You push onto the stack. You pop off of the stack. And this is not terribly hard, but it will slow down someone for a couple of weeks, or you'll have to go and look up online every single line until you understand what it does. And to walk you through Grey Wolf a little more, I'm going to spin it up and walk you through a little bit of the paces of what it does, why it's different than its counterparts of decompilers. When you come into an application, often you want to find main, which is this button. It will tunnel you down to the entry point of your executable. And here it is. This is a semi-obfuscated application that main is repointed to A. And you quickly come down here, you look at your entry point, and then you follow it step by step through your application to understand what it does and why it does it. I also went through and added things like being able to change the function, whether it's public and private, that you can simply come into someone else's application and make it public. And this is what a lot of other decompilers didn't do. They didn't quickly give you these abilities to access it. Sometimes you want to look at your function in hex, and here is the hex conversion of this function. And you can tunnel to any other function and pull up its hex, because sometimes a function is a little bit obfuscated and you have to actually jump to the hex code to manipulate it. This is the class view, and this is an incomplete application as far as being able to look at all of the values inside of the class. And this is by no means a complete decompiler, but as I go and I need another function, I come and add it into Grey Wolf. And this is a free application that I'm pushing out, and you're able to use this and not need to pay money. It does not phone home like a lot of the other decompilers, and this is specifically tuned for attacking. This will help you get into your target and accomplish your goals. A secure application. You're going to come up against USB dongles. You're going to come up against phoning home, registration checks, API calls. It's going to update off of a server, call a database, connect to the internet, and it has crypto. This is usually what you're going to find in major applications. And these are the weak spots. Anytime it comes out of the secure application to the USB dongle, you can pretty much count that they did not build their own USB dongle. They used a third-party payload, right? You go in there and you find that third party, you quickly get to where it's called in your application, and then you put a return true. When it calls out, a good programmer will segment this off to, this is the upgrade area, this is the part that we send home, and this is where you insert your data leakage, or you understand what data leakage is commonly occurring. And it's a nice place to put your backdoors because it's already connecting to the internet legitimately, so now it also adds one more encrypted call to the internet. And crypto, you can do whatever you want. You can put on a new crypto library or add a bypass to it altogether. So it can't be that easy, right? Microsoft had to do something to stop us. They put in signed code that's verified 1024-bit crypto. You're able to execute it knowing that the authors implemented this and it has not been altered. It gives you strong names and adheres to the Microsoft best practices of scoping your access to the computer. This tries to shut down tampering. You have an executable. It has a signed strong name or a DLL with a signed strong name, which is constructed out of a simple name, a version culture, and a public key token, which is a shortened public key. That's a strong name. You have keys, like I said, 1024-bit, public-private key signing, very hard to crack. Once you crack it, you're able to make your key gens, but who wants to crack a 1024-bit to get a $50 application? This lets you verify the author. Obfuscation. You have code obfuscation, logic obfuscation, shells and packers. This basically takes your executable, puts it behind a C++ decryptor that decrypts it when your application runs, and that will shut down a lot of the app decompilers, Grey Wolf included. And unmanaged calls into C++. You can write a Python shim that does your key validation. And this is all built to shut down decompiling and just what I showed you a minute ago. This is obfuscated code. It's hard to read. It's like bad named code squared because they're not using printable characters or whatever. The logic is bizarre. And instead of value equaling true, it's value equals and for equal 4. And this is basically what obfuscation is when it comes down to it. It's trying to shoot a target in a field of targets. And as you can see, it doesn't add a wall that you have to get over. It adds a little bit of time and a little bit of cognitive processing. It's search and replace. It's spending the 5 minutes to hunt down that variable, and that's what it adds, 5 minutes. Shells and packers, you have your secure application, and it just puts a wall. You're not going to be decompiling it, and that's it. However, we're going to, of course, get past that. Here is a protected application. We bring up Grey Wolf. This is a heavily protected application. It just isn't decompilable. It's either a one-off or it's packed behind a crypto C++ loader, right? We open up our application, which of course, as this talk is attacking .NET applications, this is a protected .NET app. So we inject in memory. All of those obfuscation, packer, all of that just falls away. We're past the load sequence, like I said. We simply bring in another payload. This one iterates through our application in memory and extracts the source code in memory. And here's an obfuscated function class, and we again get to our IL. This is a heavily protected application, obfuscation, shells, packers, everything they could throw at it. And we're able to inject in it, get in memory, and this is why attacking in memory is good. If you come up against a heavily protected application, you're going to need to know IL anyways. You're not going to get raw source code back, and you're going to get past anything they can throw at you. Fundamentally, once you're running .NET, you're vulnerable. But this is not different than any other application. This is the same as C++. If you get into someone else's memory space, you can manipulate their memory. It's not new Microsoft vulnerability introduced into .NET. This is just inherent into applications. I'm just lowering the bar. Instead of having to be a hardcore assembly programmer, you just have to have a decompiler and be able to look up IL and put return true. This is what you're building your applications for. Are you building a hardened application to go into an offensive environment, or are you building an effective application to go into a friendly environment? And unfortunately, most people just throw on a few shells, wrappers. We spent the $400, we looked at best practices, and now it's protected. But of course, that's why we're here, because we can make it that easy. We can blow right past any of these key checks, validation. We can, again, make all of these things that Microsoft has put in place to stop us, that all these third parties have put in place, easy. These strong name public tokens, we can just make a malicious version and simply copy these strong name tokens over. These strong names are because these keys become completely invalid when they're on our malicious code, and that is how it should work, right? However, strong key checking is off by default. So when you go into the field, you're going to find that 99.9% of computers are off by default. All of that strong name validation is just not happening. This allows us, you have an infected DLL, to infect a properly signed executable. So you don't have to infect the executable, just the DLL that it calls. This is how you turn public key checking on. It's a simple registry key. You set allow strong name bypass to 0, and now it's not bypassing the strong name. And this is also a flag you can set on your executable to say, I want this executable to compile and force strong name checking. But this gives you the ability to say, no, this DLL will now throw an error when you try and inject it, or run it. However, your executables can still be infected, and for whatever reason, Microsoft has a different mechanism for checking in Windows whether the application exe is signed properly. So you can simply, again, run your attacks against the executable and not against the DLLs, and you'll get right past that. So Microsoft, if you have keys, why not check them? Unfortunately, this is not a specific Microsoft problem. There is a lot of applications out there that should be hardened that just aren't for whatever reason. Another nice attack vector is you can run assembly code inside of a .NET application. Without dropping to unsigned, unmanaged, you can just run it inside of your application. Because inside of .NET, you can run assembly code with reflection or unmanaged calls to manipulate pointers, because in .NET, delegates, which are inside of events, are function pointer wrappers. You can simply get to that function pointer, shove your assembly code in there, and break out of all of that Microsoft security validation for the Microsoft framework when you're in assembly code. So another sweet attack vector. When you're attacking .NET, you want to know about the GAC, because the GAC is a vulnerable area that you need to take into consideration. This is what the GAC looks like. It's C:\Windows assembly. And unfortunately, it comes up a little obfuscated. You simply delete the desktop.ini, and it shows you the real GAC underneath. This is what the GAC's made out of. GAC, you'll find your installed and sandbox stuff installed into the GAC. You'll find GAC 32, which is applications that are compiled specifically for 32-bit, GAC 64-bit, and GAC MSIL. MSIL is the top-level .NET. Anything written in MSIL will compile down to run on any .NET platform. So when you're attacking your application, if it's a 64-bit, you know where to find its DLL. And of course, you can just look at it from the process. Native images, you have to know about this because when something's in the GAC, it pre-compiles a native image. So a native image is a bloated DLL that has both the MSIL and the native compiled code. This allows it to be faster and pre-compiled and not slow you down every single time you run. Native images are broken into two sections: version 2.0 and 3.5 .NET applications and 4.0 .NET applications. And there's, of course, 1.1 and other frameworks. But this is what you're going to find on most machines. You need to know this because you want to go in and delete the native image or manipulate the native image. There's a bunch of GACs. There's Windows Assembly, there's Windows WinSXS, and there's Windows/Microsoft.NET. These GACs are used by different programs for slightly different reasons. And when you check these out, you're going to find nice vulnerable areas to target this DLL, or this application shouldn't be calling .NET, but it is, and it's out of here. And the GAC is nice because everyone calls it. Even if you don't want to call the GAC, you usually end up calling the GAC anyways. Because when an exe calls a DLL, it really puts that DLL inside of the GAC, in which case it really compiles a native image. So when your exe runs, it's really calling that native image. You want to delete the native image, you want to replace your target in the GAC, and then you can hack your target from the GAC because you delete your native image, you put your infected malicious code in the GAC, and then you run it. And this is nice because someone will look at their directory and say, okay, everything's whitelisted, everything hashes, everything's good, but it's not actually running out of the directory, it's running out of the GAC. So you can infect a machine and all of the DLLs will be perfect. And it's a nice little trick that will slow down a lot of people trying to decompile what you're doing. So an exe calls a DLL, which really calls a .NET framework. This all compiles into a process. One of the nice things about .NET is everything calls the .NET framework. You infect the .NET framework, again with that fake key signing, you go through your exe, and you're in the process. You're in the process of every single application on that machine that's calling .NET. This is nice because whether it's a hard, protected application or a weak application, you're in it just the same. You're already from the framework all the way up into your process and you're able to attack it when they call toString or they instantiate a SQL connection or a thread. You simply put your shim in there. As a quick digress, I keep hammering on this because Microsoft is not going to fix it for whatever reason. Visual Studios has arbitrary code execution when you look at someone else's code. This is a fundamental feature that Microsoft has no plans on fixing. Here is an infected .NET application that you might download off of the internet. Simply, this has a Windows form that calls another user control, and when user controls are called inside of Visual Studios, the constructor is automatically fired. And this arbitrary code will happen when we look at the form. So we open the form, this arbitrary code happens, and this is bringing up a elevator that someone else wrote. Windows has some built-in features where you can auto-elevate if you're a specific known process. So gonna take this, have it auto-elevate, and of course this is what would happen behind the scenes. And we're gonna call an installer, auto-elevate the installer to admin, and now this installer is running as admin. We simply, again, install it into our computer, and this attacks PowerShell by going through and decrypting a few payloads. So at that moment, these payloads go from encrypted to viral, go in, get injected, delete the native images, come into PowerShell, and now PowerShell looks like this. This is nice because it's infected at the GAC level. It's not infected in any installed area. This is something that would take someone that had no clue what was going on days to find out. And so you can still use PowerShell, but it looks like this. And there's no way to fix this. But this could just as easily be a keylogger. This could just as easily be malicious code that sends it up to the internet, whatever you want, right? And that's what's nice about this, is you can make things that help you, such as adding Control-V insertion into it, or you can add something viral that will go and give you root access shells on whatever machine that uses it. And this is just the demonstration that could be carried out from looking at this form. So you go put a few applications on the internet that talk to credit card processing, and someone that wants to understand credit card processing downloads your application, opens it up. They're not going to run it because that would be bad form, but they look at it, they're infected. And this is something Microsoft has no plans on fixing, which I find highly dangerous, because when you're on a developer box, you have SVNs, you have databases, you have developer keys that are core to the application security. If you're able to get onto a developer box and start sending up encrypted payloads of all of this stuff, you could permanently harm a company. And you can make it so when they compile and release their application, they're actually releasing malware and viruses without knowing it. This is a great attack vector for anyone that wants to do something seriously malicious to developers around the world. You do a few thousand demo applications of XML and you're going to get a few thousand developer boxes. So this is what we're looking for. We want an application to be infected and attacked. I've showed you how to inject into a hardened application and get past it. As I said, my talks last year covered this. You want to care about this if you're not a hacker because you can defend your applications, you can defend your system, you can verify your tools. You can find out what the crypto key is, what it's sending home, does it have backdoors, is the data secure? The keylogger that I touched on a little bit, it has static crypto keys. It has 0 for its vector initialization. It has plain text passwords. When you look inside of your application, you want to take control. Don't be helpless. You want to know your threats. When you do look inside of your applications, you're going to understand the keys, the crypto, the databases, the backdoors, the malware, the technology core to your application that you're running, someone else's application that you're running. You can even get a view for how well it's coded. How many errors should you be finding? You'll find, is a validation check hard or easy? Is it A matches B, or does the password do some decrypting? You'll find data leakage. You can find out what your application is sending home. Is it sending home critical information or weak information? Is your crypto key hard-coded, or is it something more robust? You can know exactly what crypto your applications are using and what they're using it on, what parts of your data are secure and aren't secure. This is what I did to AirCrack, just to show something positive, that it's not always malicious. This is AirCrack. I went through and pimped it, and you can do this to any application. It's not necessarily malicious, but you can add new features and you can make something that's user-friendly, user-friendly. There's 2 applications, right? Protect Me and Androsa File Protector. Protect Me is completely unprotected, it's not obfuscated, Androsa is. They take 2 different approaches. Protect Me is clean, readable, concise code. File Protector is bloated, obfuscated, huge code. You inject into them, you deploy your 2 payloads. I've developed one payload that attacks both applications to show how you can make an adaptive payload that's kind of nice. I'm going to power through this last one just because running a little short on time, but I'm opening these 2 applications. I'll inject into both of them with the same payload, and instead of writing 2 payloads, which would kind of be the classical thing, I'll write the same payload for both of them, drag this payload into both, execute the payloads, and so we have the same payload running in both applications. It adaptively goes and finds a target hash value of each of them and then starts brute forcing them. These are 2 completely separate authentication mechanisms, but they both have the same exact signature. Function that takes string, returns Boolean. You just brute force it until you get it. Instead of trying to brute force a GUI over and over and over and over again with keystrokes, you brute force it with its own logic. This is why it's nice to brute force, because in this one application, it's much faster. In this other application, it's still going, because one of their brute forcing algorithms is better than the other. Because Protect Me uses good crypto, it encrypts your password, while File Protector uses, I'll get to it in a second, uses SHA-512, and SHA-512 is faster. Most backup software is vulnerable to this. Most logon software is vulnerable to this. Protect Me versus Androsa, Protect Me is better because it takes longer to brute force. Simply, these 2 applications are equally vulnerable, but they're both vulnerable to the same attack. One's slightly better. So your malware. Your malware, how do you hide? You want to use the same things that you protect your applications for. You want to use shells, crypto, unmanaged calls, protection, obfuscated code. You want to use fake signed DLL protection. And this will give your clients a sense of security that they're using valid code. You want to use intelligent names, the same as your target. You want to use the same coding style. You want to not use loops and while trues that malware classically uses. You want to not use one area for all of your variables. You want to access back into the program as their code normally would. You basically want to reuse your target and blend in as much as possible. You want to call back into your target. You want to use your target's timers, link into its events, and spread your code out into your target and your variables out into your target. This is a demo where it's essentially the same attack, except for injecting into PowerShell. I'm injecting into management console. So management console auto elevates to admin, and this program validates as admin. So you can shim Windows Management Console. I just want to give you some slight ideas of where this can be taken negatively, but you can drop shims into applications that have auto elevation to admin rights. You can attack hard applications as well as easy applications with about the same amount of effort. To attack them? Oh. It's shimmed inside of the application, so when they run it, it's not running a new process. You're actually being attacked by Management Console. So say you have a virus scanner, and it's like, oh, Management Console is trying to write to your registry. Yeah, it is. Yeah, you want to blend in with your target. When you get into your target, you want to send up data to the internet when it sends up data to the internet. You want to write to the registry keys when it writes to the registry keys. You want to blend in because in that developer idea, you're on a developer box. You're pushing out malicious code, and now every single application they sell adds registry keys that you want in there. And so it's to blend in because applications that are scanned by virus scanners are looking for signatures. One of the benefits of .NET is you're able to quickly change your signatures because it's a high-level language. If you have any other questions, I'm at the end. So, what did Microsoft do right? They didn't do obfuscation. Because if you do obfuscation, you can't vet your application. You can't read through and say, no, this isn't malicious code. No, this isn't doing bad things, because it adds that hours. I consider this to be good because I want to know what my applications do. I want to be able to vet my applications. They did good targeted security access. They did protection in computer apps. And the framework allows you to say this application does or does not have rights to write to the I/O to the disk. It does not have rights to write to the registry, and so on. They give reduced rights inside of their own code, so you can write threads that have more vulnerable code. You can scope these threads to have less rights than the rest of it. So when you're attacking it, you're trying to get into your application by some sort of code logic error that they put in there, you can scope it down. Mixed mode code is bad. If you ever drop just once to mixed mode code, so can the attacker. They can inject in there, and instead the shim is able to go to mixed mode code and break out of all of the .NET framework security. So if your application, like Microsoft commonly calls mixed mode code, it's bad. You're going to be able to destroy any of the security that they put up. The GAC and native image override, it's easy to fool people into thinking they're running valid code when they're not, and they're not doing their password validation that I noted earlier. If you want more information on the injection and attacking at runtime, I did some papers, Reflections Hidden Power and Attacking .NET Runtime Attack. You can check out my other presentations, DojoCon, DEFCON, AppSec DC, and a number of others. You can look for other people researching this area, and if you're thinking about what tools are you wanting to use for this, you want Visual Studio's MonoDevelop, you want to use Grey Wolf, Reflector, which is Pay and Phones Home, ILSpy, which phones home, and the built-in tools from Microsoft, IL, ASM, and Disassemble. And that's my presentation. I hope you enjoyed it, and thanks.